Lexi, you said you wanted to start with number 9. Is that right? Okay. So that's the cube root of 25 times the cube root of 320 plus the cube root of 3645 minus the cube root of 625. So we start by doing some prime factorizations, right? So 25 is 5 squared. 320, maybe I did 32 and 10. 10 is 2 times 5, and 32 is 2 to the 5th. So I have the cube root of 2 to the 6th times 5. Okay there? Plus 3645 is the 5 and 729, and 729 is 3 to the 5th, I think? Nope, 6th. Yeah. And then 625 is 5 to the 4th. Okay there? Okay. Now we need to do our exchanges. So the cube root of 5 squared, I can't do anything to that, so I'm just going to recopy that down. The cube root of 2 to the 6th, well, I can take all 6 of those 2's, trade them in, and get 2 2's out front. All my 2's are gone, leaving me with just the cube root of 5. I can do the same thing on the second radical, the cube root of 3 to the 6th times 5. I can cash in all 6 of those 3's to get 2 3's out front. 3 times 3 is 9. Leave me with just a cube root of 5. And then if I look at the last radical, the cube root of 5 to the 4th, I can trade 3 of those 5's in to get 1 on the outside. And I have 1 5 left over inside my radical. So far, so good, Lexi? Now, I'm going to go ahead and combine my like terms. So the cube root of 5 squared, I'm just going to leave out front. So I have 4 and 9 is 13, minus 5 is is positive 8. Happy with that? If I multiply then the radicals, that's 8 cube root of 5 to the 3rd. And I can cash those 5's in, right? I have 3 5's under a cube root. I can trade all of them in to get 1 5 on the outside, and nothing left under the radical, so I'm left with just 8 times 5, or 40. Are we happy with that? Good. It's kind of nice when they end up with no radical at the end, right? That feels pretty satisfying. Who else has questions from this? Any others that we'd like to do or see done or ask questions about? You all should have asked questions about something because I made a mistake on this. That's supposed to be negative 59. For number 6, that coefficient isn't supposed to be negative 62. It's supposed to be negative 69. I did the hard part right, and I had 59. So I did the hard part right, and the step before that, all those numbers are correct. But somehow I said that 4 minus 18 minus 45 is negative 62, which is not even really very close. So I did make a mistake there on number 6 when I wrote my answer key. Beep. You know, mistakes happen, guys. Ever happen to you? Happened to me.
So we can do the number 8 since with the
Okay.
yeah.
Those are my favorite kind of questions, where when you talk through it, you're like, ah, never mind, I know the answer. Alrighty, folks. If there's no other questions, we should continue along our journey of reducing radicals here. Everybody ready to move forward then? All right. Oops, we should say, I shouldn't say reducing, I should say simplifying. All right. So our goal today is to figure out how to do things like this. So if I have the square root of 2 times the cube root of 2, how do we do this? Well, we know that when the index for the radical is the same, we can just multiply the radicands together, right? If I have the square root of 2 times the square root of 3, that's the square root of 6. Right? We've dealt with that already. That's not how things are going to work in the square root 2 times a cube root 2. We're going to need a new plan on that one. So what we're going to do is we're going to define, thank you, make a new definition for a radical. So if I take the nth root of a to the m, this is the same thing as a to the m over n exponent. So I'm going to call this the exponential form. And I'm going to call this the radical form. So let's just do a couple of quick examples and show, to make sure we're comfortable using this definition. So let's say I have the cube root of 5 to the 7th. How can I write that in exponential form? Five to the 7 over 3. So my a is 5, so there's my a. My m is 7, so there's the 7. And my n is 3, so there's my 3. Okay. Do we feel pretty comfortable doing that? It's not difficult, right? You just have to follow the pattern of where the numbers go, right? What if we go the reverse direction? Maybe 7 to the 3 halves. What's that going to be? Yeah. So notice here that Nancy omitted saying the 2 needs to be there because it's a square root, has index 2, so I don't need to write the 2. Any other number, we would have to write that in though, right? Okay. So now that we can move back and forth between radical form and exponential form, let's talk about why this is going to be useful to us. So the reason that this new definition is super useful is we have a whole bunch of really well understood properties that we can apply to exponentials. So if I take a to the n and a to the m and I multiply them together, what do I get? We add their exponents. Why does that work? Well, if I have 2 to the third times 2 to the fourth, I have 3 2's times 7 2's. That's just 7, or 3 2's times 4 2's. That gives me 7 2's, right? Everybody okay with that idea? So just a little bit of an explanation as to why that works. So the next property is if I have the exponent of a product, that's the same thing as the product of the exponentials. So let's say I have 2 times 3 cubed. Well, that's the same thing as 2 times 3 times 2 times 3 times 2 times 3. I have 3 2's and I have 3 3's. Right? So these little examples, this is not how you would do the problem. You want to use the property to do the problem. I'm just kind of showing you why the formula that I've written down, why it holds, right? Just trying to use our definition of what an exponent means in order to kind of verify those properties for us. So if I have an exponent of an exponent, what do I do there? I multiply the exponents. So for example, if I have 2 squared cubed, that means I have 2 squared times 2 squared times 2 squared. So I have 2, 4, 6 2's. There's 2 to the 6th. Is everybody okay with that idea? A to the 0 is equal to 1, provided that A is non-zero. I'm going to come back and circle back to the explanation on that because these next 3 properties in a row kind of all are interrelated. So a to the negative n is equal to the reciprocal 1 over a to the n, again, provided that a is non-zero. And our last property that we're going to use says a to the n over a to the m is equal to a to the n minus m, again, provided that a is non-zero. Yes? Yes. So let's look at some examples here. So if I have 2 to the 5th over 2 to the 3rd, it's like 5 2s over 3 2s. So I can reduce, and I'm left with just 2 2s. Okay, so that kind of verifies property 6 for me. Now, what if it was the other way around? We would do the same reducing, and we're left with 1 over 2 squared. And if I had applied property 6 here, that would have been 2 to the negative 2. Right? And this example is for property 4. I know 1 is the same thing as like 2 over 2, right? If I used property 6, that would be 2 to the 1 minus 1. And 1 minus 1 is 0. That's why anything to the 0 power other than 0 is 1, because it's basically like just that number divided by itself. That's kind of what it means. Okay, so these examples that I gave you right here were just to demonstrate why these properties work, right? Rather than proving them, I just kind of gave you an example that kind of illustrates the main ideas of the proof rather than proving these things specifically. So let's go back and think about the problem that we were really hoping to be able to solve, which was things like the square root of 2 times the cube root of 3. So to do this problem, we're going to start by rewriting these two radicals in their exponential forms. So how can I rewrite square root of 2 in the exponential form? Well, what's the exponent on the 2? It's 1. And what's the index on the radical? Since it's a square root, it's a 2. So that means I have 2 to the 1/2. Or this 2 is this 2, this 1 is this 1, and that 2 is that 2. How can I rewrite the cube root of 2 in the exponential form? Well, that's just going to be 2 to the 1/3. Is everybody okay with that so far? I can then use property 1 from above to rewrite this as 2 to the 1/2 plus 1/3. Now, if I want to add 1/2 and 1/3, what do I need to have? Common denominator. What would the common denominator be between 1/2 and 1/3? 6. So what do I need to multiply 1/2 by to get to the common denominator of 6? Well, 3 over 3, right? And what do I have to multiply 1/3 by? 2 over 2. So that's going to give me 3 over 6 plus 2 over 6. And how do I add fractions together once they have a common denominator? Well, I'm going to add the tops, but the denominator stays the same. Is everybody okay with that? Of course. My last step now would be to rewrite this in the radical form. So 2 to the 5/6 is what radical? What's the index for the radical? 6. The radicand under the radical is 2. And the exponent on the radicand is 5. So in order to multiply radicals with different indices, we need to use these properties of exponents to kind of work around that. Let's do some more examples. Yes? Okay. So let's say I want to do let's make it the 4th root of 24 and the cubed root of 12. Notice what's different about this problem than the previous problem. What do you notice that's different, Michael? Sure. What's different between this problem and the previous problem, fundamentally? Excellent. The radicands are different. Notice all of our properties for exponents here required the same number in the base of the exponential, right? So guess what I'm going to do to start this problem? I'm going to do a prime factorization. 24 is 2 to the 3rd times 3. 12 is 2 to the 2nd times 3. I'm now going to convert each of these into the exponential form. So I have I have the 4th root of 2 to the 3rd. That's 2 to the 3/4. I also have the 4th root of 3 to the 1st. So that's 3 to the 1/4. I have the 3rd root of 2 squared, so that's 2 to the 2/3. And I have the 3rd root of 3 to the 1st, so that's 3 to the 1/3. Is everybody okay there? So we started with the problem where the radicands were different. But if we look at where we're at now, we have things where the base is the same. So we can do some multiplication here, even though at a first glance, maybe it didn't look like that was going to be possible. Does everybody see that? Okay. So I have 2 to the 3/4 plus 2/3 times 3 to the 1/4 plus 1/3. To add 3/4 and 2/3, I need to have a common denominator. What would that common denominator be? Between 3/4 and 2/3? 12. So I'm going to multiply 3/4 by 3 over 3 to get 9 over 12. And multiply 2/3 by 4 over 4 to get 8/12. Now let's look at 1/4 and 1/3. What would the common denominator there be? Still 12. So I'll multiply the first fraction by 3 over 3 and the second fraction by 4 over 4. So when I add those fractions, I get 17 over 12 times 3 to the 7 over 12. Is everybody okay with this? Now let's look at the end of this problem, or the second to last step of this problem. I'm sorry. Let's compare the second to last step of the previous problem with what we have here. What do you notice that's different between these two? Spots. There's one kind of fundamental difference here. Well, the two-number part is fine. That is a very big difference, but that's fine. The part that's not fine is that I have an improper fraction here. That improper fraction is an equivalent to an unreduced radical. So we have an option now that we've combined these things together. I can convert these into radical form and reduce my radical there, or I can stay in exponential form and reduce the radical kind of in this exponential form. We already have talked about how to reduce the radical in radical form. Let's show you guys how we can stay in exponential form and reduce the radical here. Okay? So the thing to remember is that the improper fraction in the exponent indicates to us an unreduced radical. So all I'm going to do here is I'm going to rewrite 17/12 as a mixed number. How would I rewrite 17/12 as a mixed number? 1 and 5/12. Everybody's okay with how we did that? Now that's like an elementary, middle school skill, but it's been a while since you've probably done it. If you don't remember how we did that, please speak up and we'll go through it again. But my assumption or my hope is that we all kind of remember how to do that. Okay. So what I'm going to do now is I'm going to go back and I'm going to use this property. But I'm going to use it going in this direction. So this is like my a plus, or a to the n plus m. So if I apply that, the a is 2, the n is 1, and the a is 2, and the m is 5/12. And then that 3 to the 7/12 still comes along for the ride. Everybody okay there? And so now I'll just convert this back to radical form. So the 2 stays on the outside. I'm going to have a 12th root of 2 to the 5th times 3 to the 7th. And you could type that into your calculator and turn that into just a number, but you don't need to. It's going to be a terribly big number. I'm fine with just leaving it in an exponential form like that. You could multiply that out if you want, but it's very possible that kind of like would end up having to be written in scientific notation on your calculator, and it's just kind of not worth it. But do whatever you feel like. It's okay. Let's do another. Yes? Okay. So what should we start with? Prime factorizations. 144 is 12 and 12. And then 12 we know is 2 squared times 3. 324 is about 4 and 81. 4 is just 2 squared. 81 is 9 squared, which is really just 3 to the 4th. So I'm shortcutting through some of these factoring trees just to give you a, like a glance of how we're doing it. Some of these things are things I'm just able to do in my head. If you need to write more out, that's perfectly fine. expectation is not that you're shortcutting through as much as I am. I'm just trying to move things along because you don't need to see me like break down these factor trees over and over and over again, right? Everybody's okay with that idea? Okay. So I have 2 to the 4th times 3 squared. Oops. Said 2 to the 4th. I did not write that though. Then I have the 5th root of 2 squared times 3 to the 4th. Yes, of course. I'm now going to rewrite these in exponential form. So I have 2 to the 4/3 times 3 to the 2/3 over 2 to the 2/5 times 3 to the 4/5. In this problem, I'm going to use property 6 because I'm going to combine them. The 2's and 3's are in different levels of my fraction. So that's going to be 2 to the 4/3 minus 2/5. And then 3 to the 2/3 minus 4/5. To subtract these two fractions, we need to make a common denominator. What would the common denominator be between thirds and fifths? 15. So the 4/3 I'm going to multiply by 5 over 5. And the 2/5 I'm going to multiply by 3 over 3. Similarly, I'm going to do the same thing here. So I multiply by 5 over 5. And then multiply by 3 over 3. So when I do the subtraction, I get 14/15 and then -2/15. Is everybody okay here? Okay. Now I'm going to have to use property 5 because I have a negative exponent. Remember, the negative exponent makes a reciprocal. So when I multiply those together, oops, I get this. You're back.
Yeah.
Everybody's leaving early today. Julia, this is your ticket out of here. Guess you're late. It's for in the past. Now we do have a little bit of an issue with this. This is not going to be our final answer. Can anybody take a look at this and see what the issue is? There's still something more we need to do. This is the issue. Why is that an issue? That's the same thing as having a radical in the denominator, isn't it? Everybody agree with that? So if I have a fractional exponent in my denominator, I need to get rid of that, just like I would have needed to get rid of a radical in my denominator. So looking at 3 to the 2/5, what's the next whole number after 2/15? It's that easy. 1, right? That's the next whole number after 2/15 would be like 1, right? 1 is the same thing as 15/15. So what I'm going to do is I need how many more 15ths? 13. Does everybody see why? So I'm going to do that to the top and bottom. So that's going to have 2 to the 14/15 times 3 to the 13/15 all over 3 to the first. And then I can just convert back to radical form. And that's definitely one I would not want to type into my calculator. That is a big honking number there. I think 3 to the 13th itself will probably give you something in scientific notation, let alone multiplying by 2 to the 14th, which is also, you know, quite large. Let's do one more example, and then we'll call this good for today. Sound okay to you guys? All right. Of course. All right. A lot of stuff going on here. I'm just going to write in the prime factorizations. Is that okay with everyone? Rather than drawing the trees at all. So we have 2 to the 3rd times 5. We have 3 squared times 5 squared. We have 2 to the 5th times 3. And then we have 2 to the 3rd times 5 squared. All right. Let's rewrite these all in exponential form now. So I have 2 to the 3/2 times 5 to the 1/2 times 3 to the 2/3 times 5 to the 2/3 over 2 to the 5/4 times 3 to the 1/4 times 2 to the 3/5 times 5 to the 2/5. Is everybody okay there? For the 2's, I'm going to use properties 1 and 6 at the same time. So that's going to be 2 to the 3/2. And then I'm going to have to minus the 5/4 and the 3/5. Everybody see why I'm minusing those two? Because they're in the denominator of the fraction. Now we'll do the 3's. Here I have just property 6 because I just have a 3 in the numerator and a 3 in the denominator. And then for the 5's, I'm going to be using both property 1 and property 6. So I'm going to have 1/2 plus 2/3 minus 2/5. Is everybody okay with where we're at here? Okay. Common denominator time. What's the common denominator between halves, fourths, and fifths? 20, right? So I'm going to get 30 over 20 minus 25 over 20 minus 12 over 20. Between thirds and fourths, the common denominator would be 12. So I have 8 over 12 minus 3 over 12. And then halves, thirds, and fifths, what would the common denominator there be? 30, right? So 15 over 30 plus 20 over 30 minus 12 over 30. So 30 minus 25 is 5, minus 12 is negative 7/20. 8 minus 3 is 5, so I have 5/12. And then 15 plus 20 is 35, minus 12 is 23. Oops. 30. Everybody okay there? Notice that I have the negative exponent here, so that's going to make a reciprocal. So that's really just going to send, oops, this guy to the denominator. Everybody okay there? Okay. Now, I can't have that fractional exponent in the denominator, so I need to fix that. So I'm going to ask myself, what's the first whole number after 7/20? 1. How many more do I need to get to 1? 13. Everybody good with that? So I'm going to multiply the top and bottom, 2 to the 13/20. Are we okay there? Okay, the last thing now is I need to get all of these things under the same radical, so I need them all to have the same common denominator. What's the common denominator between 12, 30, and 20? 120 is a common denominator. 60, though, is the least. So let's use that. So the first one I'm going to turn into, I have to multiply by 5, so 25 over 60. And next one I have to multiply by 2, so 46 over 60. And the last one I need to multiply by 3, so 39 over 60. But I'm not going to add these numbers together. Why not? The bases of these exponentials are different numbers. You cannot combine them. Instead, what this is going to allow me to do is put them all under a 60th root of 3 to the 25th, 5 to the 46th, and 2 to the 39th. Do not try to type that into your calculator. Goodness gracious, it's going to give you an error overflow on that one. But we can do this problem without the calculator relatively easily, right? Okay, let's stop here.